Welcome back to this last chapter on differential equations. So for this video, we will take a look at the logistic equation. The growth model we have studied applies to populations that are allowed to grow freely without external influences. Now, most population growths will tend to be limited by certain factors, like food supply or the size of their environment. For example, if a small number of rabbits were introduced into a small island where there are no rabbits and no immediate predators, well, we may expect the population to grow exponentially. But that would not be realistic because the population would be limited by food supply. So suppose the island actually has enough food to sustain a population of L rabbits indefinitely. We could expect the growth of the population to be proportional to the number of rabbits at that time, as it is in the original growth model. But this would only work if the population P is quite small. As P approaches L, we would expect the rate of increase to approach 0. Our one such model is the differential equation dp dt equals Kp multiplied by 1 minus P over L. This differential equation, quite famous, is actually called the logistic equation since it models growth that is limited by the supply of necessary resources. The key factor here is 1 minus P over L. Indeed, if P is less than L, so we will have that, well, P is less than L means that this P over L is less than 1. So 1 minus a number less than 1 will be greater than 0. So the rate of change will be positive. On the other hand, if P is greater than L, then 1 minus P over L will be less than 0, and the rate of change, dP over dt, will actually be negative. We can see that in the case where P is actually equal to L, then this actually factor is 0. And then there is no growth, no increase, and no decrease for the population. So the logistic equation actually is a separable variable type of differential equation. So it can be solved using our four-step approach presented earlier. Obtaining the solution is not kind of very difficult calculus-wise, but the algebra to arrive there is rather cumbersome. So let's go over the steps to get the solution to this differential equation. Starting with dp over dt equals Kp times 1 minus P over L, we take a common denominator of this, and we get L minus P over L for the bracket. Dividing both sides by all the p's on the same side, that is, we actually get this new version, L over P times L minus P, dP is K dt. Now, if we integrate both sides, we notice that the left-hand side actually is a partial fraction. I haven't seen that in a little while. So let's go aside and let's handle the partial fraction. L over P multiplied by L minus P should be broken as a case 1 as A over P and B over L minus P. So we take a common denominator, we group the terms together, we solve this in terms of A and B, and we get A equals 1 and B equals 1. So you can verify quite quickly that L over P times L minus P is nothing else than 1 over P plus 1 over L minus P. So back to the integral. We have that the integral of L over P times L minus P dP is the integral of K dt. So now we know how to rewrite this using partial fraction. It's integral of 1 over P plus 1 over L minus P dP. Here we take the K out, and we integrate the integral of 1 dt to be Kt plus C. As for this one, well, the integral of 1 over P is ln P, and the integral of 1 over L minus P is ln of L minus P with a minus 1 inside. We have a shortcut formula we know for that. Now remember that the ln of u minus the ln of v is the ln of u over v, so we bring into 1 ln, and we get rid of the ln by raising both sides to the power of e. So that p over L minus P is equal to e to the kt times e to the c1. Well, I wrote c1 over here because I knew that I would want to rewrite e to the c1 as one single constant c. So what do we get here? We get that p over L minus p is equal to c times e to the kt. I'm going to cross multiply L minus p to the other side. I'm going to multiply this in. I'm going to collect my p's on the left side, factor it out, and get that p times 1 plus c e to the kt is actually equal to lc e to the kt. I'm going to divide both sides by the bracket, 1 plus c e to the kt, which will actually give us e to the kt on top times cl. And I'm going to factor out e to the kt from the denominator. I'm going to get e to the minus kt plus c. Canceling the e to the kt top and bottom, I actually get that p is equal to cl over c plus e to the minus kt. So I'd like to introduce p0 in there. So I'm going to let p0 be the population at time 0. So I'm going to let t is equal to 0 in this equation. The only place where there's a t is the exponent of e, so e to the 0 is 1. So p0 is cl over c plus 1. I would like to isolate the c from there. Bit of a tedious algebraic exercise, but we should do it. So cross multiplying c plus 1 to the other side, multiplying the p0 in there. So collecting the p0 here, I'm getting actually collecting the c's on one side, and then factoring out the c, I get that c is p0 over L minus p0. Putting this back into our original equation 1, we actually get that p is equal to cl over c plus e to the minus kt, but I'm going to replace c by p0 over L minus p0. And I'm going to get this relatively nasty equation. So to simplify it, I'm going to multiply both sides by L minus P0. So multiplying both sides by that. Cancellation here and here, cancellation here and there. So P0L is P0 plus L minus P0 times e to the minus kt. So factoring out a P0 from the bottom, I factor out P0, I get 1 here, and since this has no P0, I'm going to write it as L over P0 minus 1. And that is actually the final form of the solution after the P0s are canceled to the logistic curve. So that was actually quite an interesting exercise in terms of algebra. Let's see how we can actually put that in practice with, applied problems. For the purpose of the following problems, we will denote L to be the actually carrying capacity. Suppose that a population actually develops according to the logistic equation dp over dt is equal to 0.05 p minus 0.0005 p squared, where t is measured in weeks. Find the carrying capacity and the value of k. So taking this equation and actually factoring out from it 0.05 p, I get in the bracket 1 minus 0.01 p. Now, I know that 0.01 is the same thing as 1 over 100. And that now fits the differential equations that we had to begin with. We can actually see by looking that k is 0.05 and L is 100, simply by comparing. Another example, suppose that a population grows according to a logistic model with initial population 1,000 and carrying capacity 10,000. If the population grows to 2,500 after 1 year, what will be the population after another 3 years? So this time we're using the solution to the differential equation of the logistic equation. So we get the answer that we worked quite hard to get. And then we're going to replace P0 with 1,000 and L with 10,000 right back into this equation. So we'll get 10,000 on top, and here we're going to get 10,000 divided by 1,000. So we'll simplify this kind of nicely. So this is actually 10 minus 1, so it's just really 9 e to the minus kt. Now, if t is 1, p is 2,500. So we are going to put that in. So 2,500 is my population, and my time t is 1. So I'm going to divide the 10,000 to the other side. 2,500 divided by 10,000 is 1/4. I'm going to crisscross, cross multiply, move the 1 over, so 4 minus 1 shall be 3. Divide both sides by 9, so e to the minus k is actually 1/3. So minus k is the ln of 1/3, getting rid of the e. Now, remember the old log rule, ln of u over v is again ln of u minus ln of v, so that's ln of 1 minus ln of 3. ln of 1 is 0, so minus k is minus ln of 3, which gives us that k is just ln of 3. So the current solution to our equation is 10,000 over 1 plus 9 times e to the minus ln of 3 times t. Now, remember the question, what's the population after another 3 years? So another 3 years from the 1 year where we were takes us to t is equal to 4. So we plug this back in, and we basically solve for p. So the good way to solve this is to use the rules of exponent. So we're going to put the 4 here. The minus and the 4, why don't we put that in front and bring it as an exponent, sorry. So e to the ln of 3 is actually 3. And 3 to the minus 4 is 81, 1 over 81. 9 times 1 over 81 is actually 1/9. And 1 plus 1/9 is 10/9. And if we flip the fractions, we get that the population will be 9,000. And this concludes the last problem we wanted to look at in this chapter of differential equations. Take care and see you soon.